initially we started with the convolution. We did the types of convolution, right? The representation. We tried to solve the problems and calculation. Then we did the programmatic approach. We tried to solve the convolution with respect to the writing the code from scratch for one-dimensional and using the various tools that are available, right, inside the modules, such as NumPy, SciPy, etc. Okay, then we had a quick look at the various learning rules. Specifically, we started with the delta learning rule. We are going to learn about a few more learning rules in today's session, but just to visualize what exactly is meant by the various schemes to update the weight. We know that there is a learning rule, but when we say that we have a learning rule, with respect to a learning rule, there are various schemes to update the weights. So in order to understand that, we looked at we considered the delta learning rule, right? So just try to remember our discussion in the previous session, right? So these are the equations corresponding to the weight update, right? This will be such equations we are going to get for various learning rules. Irrespective of which learning rule, you are going to get some equations like this. Again, this equation has a specific part that is governed by the activation function, right? So we need to define which activation function we are going to use initially, right? So that needs to be decided because equation will use that derivative of the that activation function as well, right? So we know all this. Because of that, we we could write the code ultimately because we know the steps, right? Before that, we need to choose what is a scheme. So we considered three various schemes, right? The first one is a stochastic gradient descent. It's the simplest one. Every time you give an input, you update the weight, right? That's the logic. Then there is what is called as a batch, right? We understood that you don't have to update the weight every time you use a training data. You can hold on, you can keep calculating the values, you can keep accumulating the weight update value. Whatever weight needs to be changed, you keep accumulating that. Right? So at the end of one set of training data, one epoch, you will perform the training. Right? So whatever accumulated value you have, try to take its average and we can use that average value to update, right? So that's the second technique, and the third technique, it's much easier to implement as well as to analyze, right? I don't have to even wait for the whole batch to get complete. Divide the batch into mini batches, right? Every batch you try to perform the weight updation, right? So then we try to define epoch. Anyway, we are very sure of what is an epoch. Then we consider an example of a stochastic gradient descent, right? We consider it data, it's a binary classifier, right? We try to define a simple neural network because we want to understand the process behind that, right? So just it's easier to implement in a simpler way rather than going for a complicated. All right, but today's session will be slightly more complicated than the yesterday's session because you see, we are not going to use a simple network like this. Slightly, we try to bring more neurons, right? So not very complicated one like many hidden layers. We are not going to touch that, but still, okay. So slightly complicated than this. So code will be slightly lengthier than this. We require all the basics we discussed in the yesterday's course as well. So, right, so just try to remember there was a sigmoid function, activation function written. We used our own code and we defined a delta learning rule using SGD technique, right? So for that also we wrote a code, right? You can see the code here. Then we tested that, right? In which part you define what is your input, what's the desired value, and right, define the weights over here, do the training, decide the number of epochs you want to do, right? And get the updated weight and perform the testing part and get the output. So we could observe that the output is pretty much closer to the desired value. So 0011 was required and we could get closer values. And the second approach was to implement the same thing using batch, right? So you can see that we use a term called DW sum. So that this DW sum fundamentally is used to accumulate the values of the DWs, delta W values. So those got accumulated, and at the end you see DW average was taken, dividing the sum, that is DW sum, by the number of training samples. In this case, it is equal to n, that is 4. Then we updated the weight, right? And we returned W, right? That's the only change compared to the previous method. And we could check the same similar on the similar lines of code. We could test this method as well, and right, we can say that yes, this is also going to do a similar job, right? But maybe the number of epochs are different, right? So some differences we have, right? So this is what we discussed in the previous session. All right, so moving ahead, so our today's objective will be continuation of this. So uh, okay, let's start like this. So first thing, anyway, we have two methods, two functions. One is a SGD, one more is a batch applied for a delta. So our first objective today will be to make a clear-cut comparison. I want to say that I will do only say 500 epochs, and within that I want to see the uh, okay, I want to judge which one is better, which one is performing better, because initially if your learning curve is better, right, then you are going to apply that because that has learned more with less number of iterations. But because now anyway we understood that the second one took 50,000 iterations, so I am expecting that that is performing slightly lesser compared to the HTTP, because weight updation happens regularly. But when your computation is too large, right, maybe you may have to compensate a little bit, right? So that's what we are going to use at a later stage when we go for the practical applications. Okay, as of now, for a simple network, let's try to make okay, we'll try to write a code that compares, right? So comparison happens in terms of the error. uh, we have defined the error earlier, that is the desired value minus the current output value. What we do, we'll try to keep accumulating the error itself. That's first point. And at the end, with respect to the epoch wise, or the number of iterations wise, at this iteration, this was the error. Like that, we try to make two arrays, one for the SGD technique and one for the batch. So the learning rule will still keep same, right? I want to, this comparison, this is actually a part of yesterday. I couldn't go faster to finish that. That's why, right? But this is very important. So we have to cover. All right. So we'll cover that today, and then we'll proceed with the next topic, the next learning rule, and what are the issues with this learning rule, if any, we'll see. Okay, then we'll proceed to that. That's our idea. So you can see here initially the same codes I copied from the yesterday's notebook which we had, right? So I'm going to give two notebooks corresponding to each of the class, right? That will be shared to you in through the LMS. All right. So today's notes will be with today's date. Okay. So in class coding 10/7/22. So it will be shared by this time. So just see that the same codes which we used, right, in the previous session, it has been copied here, right? So like let's start with the coding, right? So what we can do, uh, initially, let me start with the definition of my arrays. All right, so I want to go with the arrays. So X is my data. X is equal to it's np dot array. Let's create the arrays like we did earlier. We had four different. I'm going to still use the same data set. I'm not going to change because four four different data points are enough to understand the whole concept, right? I don't want to make this complicated now itself, right? But anyway, ultimately we are supposed to check the complicated what you call concepts as well. But anyway, so as of now, let's keep it simple. Okay, so this the second data set, the data point will be 0, 1. Okay, that's the second data point. The third data point is 1, 0, 1. And let's move further to the fourth data point. That will be 1 comma 1 comma 1, I guess. So yes. Okay, so this is the data point. Now let me define the D as well. Okay, so D is equal to, it's a desired or the target values, right? For corresponding to each of the values over there, we'll define the D like yesterday. Okay, so this is np dot array. So first two belong to the class 0 comma 0, and the next two are belonging to the class 1. So this is the D. Then let me write the weights. W1 is equal to, right? I just explained why I write like this in the previous session itself. So simply I'll follow the same thing. Okay, this is np dot I'll go for rand, right? So that I can get both the positive as well as the negative values. Okay, so np dot random dot rand, it's one rows, three columns, right? Because as you can see the X data set goes row wise. Each row has three columns. So that those three columns will be considered like when I give it to the machine, right? It gets converted into a column matrix which has three values, right? So like first row has 0, 0, 1. It's entering into the machine. So I need three weights. Okay, so you can see that the weight is also one. It's considered because it's a row wise. This is, you can consider vertical arrangement. So this goes into the machine. So wherein the machine should have three weights. Okay, one row, three columns. Right. So definitely you can think in a different way and convert this into a column matrix, and you can give it to the machine. Right. So it's left to you. It's all decided by the program. So try the other ways also, because you may have to get comfortable with the row wise representation, column wise representation, etc. Okay, right. So this is the row wise computation. So what I do, say maybe I'll write -1. That's one weight. I need two weights now because I'm using both the algorithms. All right. So separately I'll give the weights. So I'll just copy this and let's paste it. Okay, so you can see that the weights are defined. Now you see, let me fix the number of iterations, because I don't want the whole process to go all the way till 10,000 epochs, or right 50,000, like that. Within a lesser number of epochs, I would like to, I want to plot and see the error. Whichever method gives me lesser error, that's the one I can decide that it's the best. Okay, so that's our objective. So I don't want to go till 10,000. Let me keep a smaller number, say 1,000. Okay, so within 1,000, I think 500 is more than enough, but machine is faster. So changing 500 to 1,000 actually should not matter. So I'll keep it as 1,000. So what I do, I'll create two arrays to store the error values I'm going to get for each method. So one for the SGD technique, one for the batch technique. All right, so let me call it as, say, first one is E1. So let's say E1 is equal to, it's again the NP dot, you see pre-allocation of the memory is going to be pretty much faster. We already know that particular concept, right? So I'll just use NP dot zeros, right? So you see, I want to create an array of 1,000 rows and one column. Let's see. All right, so that's what will happen for this. Similarly, I'll write the E2 as well. Okay, E2 is also equal to, we'll do the same thing. All right, so we have the two arrays, right, with zeros as initial values assigned. Now we have the data set ready. We already have the functions written, right? So I just have copied and pasted it over here. So we don't have to wait anything. Directly we can start with the epochs, right? And call these functions so many times. In each iteration or epoch, you calculate the error. That's our fundamental idea now. So we'll go for a for loop, right? For epoch in range, right? What's the range we decided? I think 1,000 I just mentioned, I guess. Yes, right? So 1,000. So within this 1,000 epochs, do the following, right? Calculate one of the weight W1 from SGD, calculate another weight W2 from the batch method, right? So I just have to just look at this calling technique. Delta batch is one function, delta SGD is the other function. Okay, so let's let me use some spaces so that I can. All right. So this is what's going to happen. No. Yes.
So
Yes.
can I interrupt?
Yes,
So
please.
yeah, one is like okay, D array, whatever is the like okay expected output that needs to be transferred, transpose, and the second is like okay for weights, if we are going to like okay generate it randomly for weight one and weight two, then the maybe the in a comparison for one, if we use a weight one, the initial weight one, and for a two, the starting point might be like okay different. Then comparison might have like okay little yeah. So can we like okay use the same weight starting weight for both so that the comparison becomes more valid, so that we or what I can say apple to apple.
No problem. That's possible. Definitely. Yes.
Yeah.
So okay, coming to the transport part, I think okay. If you go back to the base, yes, we can write a T here just to understand the purpose that okay, this needs to be transported, right? So that's okay. But if you try, right, if I create an array np dot d is equal to np dot array like this, I print it, it will be a row representation, right? Then you take d dot t, it's a transpose, it will still show the same thing. Okay, so whenever the dimensional, it's actually, if you consider this whole what you call all the four elements will be considered as, right, a single element for d. D has only one element. It's not having four elements, right? So going back to the basics of NP, I'm saying, right? Okay, but yes, what you told is right. It has to be dot T, but for this particular machine, right, it doesn't matter when the elements are just one, because as I told, this whole array will be a single element. We understand that okay, it's like there are four elements, but what machine considers in under the NP numpy is that, right, it's a single element. Okay, so considering that, even if you miss a T over there, that doesn't matter. I hope that point is clear. Okay.
Yes.
Yes.
Thank
okay.
you.
Sure. Right. So we'll resume. Yes, both points, whatever you mentioned, are perfect, right? We can that. But anyway, let's go with the comparison and then we'll come back. Okay. Yes. Fine. So we have done this. Okay. Let's call them. Call the functions. Say w1 is equal to the first function. I forgot. Right. Okay. This is delta sg. All right. So I'm going to call that. It's delta. Okay. Delta sgd. You will pass the arguments in the same order. So the weight, then I will pass a x, and I'll also pass the e. Okay, then we'll call the second function, that is equal to the delta batch, pass w2 x and d. Right. Okay, so right, I think we will get the updated weights to w1 and w2. Right, now in each of these epochs, right, there will be an error generated. Okay, depending upon the method you use, you will calculate an error. Right? We need to put that into the even at a later stage. Directly inside this loop, we are not going to substitute that, right? So what we do, I'll create another what you call say variable. Say this is small letter, maybe es1 equal to 0. For another method, I use es2. Okay, that's also equal to 0. Let's say. Okay, now I know that the number of data samples I'm going to use equal to 4, right? I'll directly use that. So go for another for loop, because inside out of these 1000 times, each time you're going to pass the 4 data points into the machine, right? So for say I in the range n, so do something. So what's that? I have an X available. Take one of the X from that, right? So take it row wise. So slice your X. So that has to be, say, small x is equal to capital X of ith row, and take all the columns in it, right? So this is the same slicing we did yesterday. So I think this should be fine. So from D also you do the same thing. Okay, this is D of the ith element, right? Like 1 by. Okay, then let's say after D, I should get a partial output by multiplying W into X, right? So let's do that. So I think we will call it by two names because two methods are there. So one of them is V1. V1 corresponds to the W1. So as we can see, W1 is being trained by the SGD technique. All right. So corresponding to that, we will be writing in this fashion. Okay. So V1 is equal to, it's a multiplication. So NP dot, right? It's a mat mul. Yeah. Okay. So mat mul, use W1, W into X, right? So W into X. Fine. Then once I have a partial output V, I should pass it through the activation function to get the final. So Y, we'll call this is Y1. Okay. So is equal to, I think we have a my sigmoid function defined, right? So through that you pass V1 to get a Y. Okay. Now we had calculated the error, right? So I think in this case, I'm not going to call as E. It's, say, I think we named it as ES. Okay, ES1. So okay. So let's use this ES1. Previously we had written, I think we had written D minus Y, I guess. D minus Y. According to the same notation, this would be D minus Y. Okay. So I have a question here. Can I use the same ES1 if my intention is to accumulate the error? Okay, so because you see, epoch number 1, I get a ES1. Epoch number 2, I get another ES1. Okay, every time I do that, I get a ES1. My intention is that I want to accumulate, right? Because this is going to happen 4 times, right? Inside this loop, this is going to run 4 times. After the 4 executions or 4 times, so for I in range. Sorry. Okay, so I continue with my question. So this inner for loop runs 4 times. Each of the time I'm going to get a error. Let's assume the SGD technique. And if I try to write the ES1 in this form, the D minus Y, and I try to accumulate that, will there be any effect on whatever is my intention? My intention is to take a total error and plot it at the end, right? So keeping that in mind, if I keep the error in this format, if I try to keep the error calculation like simple one, D minus Y, will it affect in some way that that will not help in understanding or implementing whatever I'm intended to do? So that's my question. So please think over it. You have, say, 1 minute of time. Anybody has an answer, please give me an oral answer. So ultimately, my question is that should I change this error and convert this into some other form, or is it okay? Yes, anybody?
Yeah, so basically there are two things. One is like, okay, here we are working with the absolute error. So it may happen that like, okay, if we accumulate it, then it might become like, okay, a zero. So that's why we want to like, okay, use something called like root mean square or some type of that, so that we get the yeah.
That's good. That's very nice. So the same concept, right? So this ES1 can be negative as well, right? So I keep accumulating. So initial few values were positive, right? Error increased, okay? But after some time, maybe the error became negative, but still there is an error, right? So I actually am supposed to consider the magnitude part. So, right, many types of errors can be brought in. So I still would like to keep it in the simplest format. I'll simply square it so that even if it is a negative error, it becomes positive. So so that I can keep accumulating. I hope that's clear, right? So what I'm going to do now, I will not use this. So I will keep accumulating to the same variable es1 plus equal to. So let's do this. This is d minus the y1. Let's square it. All right. So that's how I calculate this. So let me remove the space here. So just to understand that, okay, this whole thing is one block that corresponds to one of the neural network which implements the SGD. Similarly, let's proceed and calculate the batch processing. So the V2 is equal to its NP dot matmul. I should use W2. All right. So W2 input, then call it as a y2. Let us say y2 is equal to, this is my sigmoid, and pass v2 to that. Then do the same thing. All right. So es2, I guess. Okay, that should be equal to no, plus accumulate, right? So this is equal to, like the same, there is a d now. From that, subtract the y2. All right. So this happens inside the inner for, right? Once this is done, all the four methods have been, all the four of them have been, right, calculated, and sorry, four iterations will complete, and we have the ES1 and ES2 that got accumulated according to the method.
So, sir, I have one question. So, why are you adding the error value to the, like, instead of assigning?
You see, the capital E1 is the error of that whole epoch, like epoch number 1, 2, dot, 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 up to 1000. Okay. But the capital E1 I can assign once I have all the ES1s calculated for all the four inputs. Correct?
Okay.
The small ES1 and ES2 are the errors of that machine, right? For all the four inputs. Because that is when you give all the four, one iteration, one epoch is complete. So I calculate that in ES1. Now you see, I'll assign that to the E1. Once this, I am out of this inner.
But I think there is a difference between the error that is calculating in the like in the batch scheme and the other SGD method.
Yeah, you see.
Because in SGD we are adding the error like in every iteration, I think.
That's correct. That's correct. But once you consider the whole epoch, right? I'm considering the whole epoch, right?
Yes, you considering.
This is being considered for whole epoch. So irrespective of the method, we are considering the error that occurred for a whole epoch, because I don't have a common thing to compare both of them, so I have to make it. So now my idea is that, okay, calculate the error irrespective of the method. Take one complete iteration, right? Sorry, one complete epoch where all the four data samples will go. There is some error, right? It can be irrespective of the method you use, you get some, right? So let's compare that. Because as you told, there is no common base, right? Because both methods work in a different direction.
Yes, right.
That's why here, in order to make a comparison, I have to do my own standard, right? So that this is what I'm using. Definitely there are other ways, right? You can think of, right, whatever you think, right? Okay, this might work. Please try that. Okay, that's what is mine. I hope that's clear.
Okay.
Yes, sure. Now you see, I'll update. So that is E1. I think we'll give the name E1 and E2, right? Okay, so E1 of a particular epoch, because this corresponds to the epoch only. So for the first epoch, so this will be E1 of epoch. This is equal to, again, I'll try to do a normalization. So that might take care of the total error that might occur, right? I divide by 4 because you see, this is the averaging part where I added the 4 samples, right? Errors, and I'm dividing that. So something like SGD and the this batch method, they might become equal, right? Their the working might become equal. We are thinking in that way. That's all. Okay. Maybe we are trying to bring them into the same standard by dividing this error by 4. All right. So that is nothing but, you see here, I got an accumulated value ES1, and I'm dividing that by n here. Similarly, I'll do E2 is E2 of the certain epoch. Right? I'll say this is also equal to the ES2 divided by same. Right? Even if I keep it same, anyway, only the magnitude is bigger. That's all. Now it got divided by 4, so smaller value. That's all. Other than that, right? No change. But again, this is something like a normalization. That's all. Averaging part. Okay, so we are still inside this for loop. I think for a given epoch, where is it? Yeah, epoch number 1, I get E of 1 and E2 of 1. So that finishes first the loop. Once again, I go back. I'll come back to the for loop. Epoch becomes 2. So once again, everything is calculated. You have epoch of 2 equal to some value. Epoch, right? Sorry, E2 of epoch is some value. E1 of epoch is also some value. So like that, we keep accumulating that. It runs 1000 times. I will be filled with these two values at the end. Okay, fine. Then now, okay, did I bring in the matplotlib? Yes, we have the matplotlib there, so I can directly try to plot it. So png plot. Let me go to the E1. I want to bring a legend, so I'll give a label as well. Okay, so label equal to the HGD based error. Okay, so then I'll go for png dot plot. Let's plot the E2 now and give label equal to the batch technique. Corresponding to that, we have some error. Then I'll go for X label. So along X axis, it actually gives a count for epoch. All right, so I'll just write epoch. Y label equal to, this is the error. So during the training, we are actually computing this error. So I'll write training error. Right, I'll also bring the legend pld dot legend. Okay, so now let's try to run this and see what's going to happen. All right, so as expected, right, one of the points which was raised at the beginning, that because of the difference in the weight, will there be a difference? Yes, there will be a difference, right? So that's also going to matter when you are going for a huge data set with a huge number of iterations. All right, so at least when you have a huge data set, right, yes, it's going to matter. So we have to make sure that you keep the similar weights, right? So but since this data set is smaller and number of epochs are also less, right, as of now it doesn't matter, because our intention was just to compare within, like as I told, 500 was sufficient, right? Because you can see that within 500 means I'll be somewhere here, right? So within this itself, I'm able to judge which is the method, right, that suits better. So error is high for a given epoch, right? Consider any epoch, fix your X value, right? I can see that during the initial phases of training itself, SGD has lesser error. In the sense, it is learning quicker, right? So you see the learning curve is much steeper over here compared to this state. All right. So this was our intention, just to understand that, okay, which technique we are supposed to adapt, and we want to make a comparison, right? So again, when you go for a mini batch, right, that's also going to perform, right, somewhere closer to this. Okay, so we, again, depends on the data set itself, but in general, this will perform somewhere like this mini batch. Okay, so this is what is expected. When you write a code, you'll be able to see that as well. Okay, so once you get this particular code and you have written the let's say the mini batch size, you implement that also with this, right? Just add that part of the code to this and check, all right, and print it. Okay, so any doubt with the discussion so far, right? Please let me know, otherwise we'll move ahead to the next topic. No doubt? All right. Then let's move on to the next topic. All right. So the next topic we are going to is, okay. So here just the idea, right, for you to think, right? So this actually is actually a single neuron, and we know that what are the drawbacks of a single neuron? Like only one layer, right? There is no hidden layer. Input goes directly to the neuron. Neuron provides output. We already have discussed in the previous sessions that the main problems with this kind of network is that it is capable of classifying those data points which are linearly separable. Correct? So this data set which we have considered is actually a linearly separable, right? So one thing for you to do is that once you get this code, right, just change, make sure that this data set, right, becomes a non-linear data set. So X remains same, only D you change, right? So instead of 0011, change it to something, so that, right, the classification, the desired data becomes a non-linearly separable data. Okay, so that's a homework part, right? And right, just see what happens. What happens to the machine's performance? All right, that's an important thing, right? Right, do that and come back with doubt. Right? We'll discuss further when we have time. Okay, so as of now, I'll move further. So the next topic we are going to discuss, this is where the things are going to become very interesting, which leads to the which brings us closer to the convolutional neural network. Okay, so the very important and very interesting learning rule, right? I'll change the learning rule. It uses the delta only, because that's the motto behind starting from the delta itself, because the one which we are going to use now, this is the most widely used, and people always get confused what exactly is happening here. All right, so the name you already have heard of, as I know, right? So that is called as, right, the error back propagation. Right. Again, this is applicable, right? We don't see the error propagating back in the delta rule, because there is only one neuron. You calculate the error there and you deal with the error there itself. Okay. That's why the fundamental idea of a error back propagation was not observed so far. Right. Now we'll move to the next type, where I know the reason why I go for a multi-layer, right? So we already have discussed, right, in the initial phases of this same module, right? So now let's directly jump into the case that I have understood that, right, the data set I have, right, is non-linearly separable. So I cannot use a single neuron, right? So I will decide that, okay, let's go ahead and let's use multi-layer. So in this case, it's just an example. You can see here, right? We are considering a specific neural network which has two neurons at the input, two neurons in the hidden layer, okay, and two neurons in the output layer, right? So x1, x2, the standard notation, right? Both will go to the input neurons, right? And again, we are considering, right, it's actually fully connected layers, in the sense this neuron is connected to both the neurons in the next layer. Similarly, you can see that this neuron is also connected to the both neurons. So there is a fully connected layers. Same thing is true even here. Okay, so that is what is the representation. And now let me give you the equations corresponding to this. Right? I hope you have studied how the matrix representation works for a neural net. Okay, so that's what I want you to recall. If you are not able to recall right now, I'll give the equation. So once you see the equation, I think that should be fine for you. Right? So just look at this equation, right? So how the weights are being calculated, and see this V1 and V2 are, you know that we have used the V1, V2 earlier, correct? So the same V1. So this is the partial value, V1 and V2. Okay, V1, V2 comes from this point. I need to activate this further so that that value partial V1, V2 becomes equal to activated value, and that activated value will be passed on to the next layers. Right? Okay, just make this thing very clear now. So this is simply W1 into X. What is W1? All these four weights are written as, right, a block where you can write, okay, this is W1. Right? So you can think that the W1 is the weight of all the connections that lead to the first hidden layer, in the sense from the input to the hidden layer. All right, so that is denoted as W1. You can see the coefficients. I think this part I have discussed earlier. So W11 and W21, right? It means it's going from the first input neuron to, right, corresponding neurons in the first layer. So this W11 and 21 suggests something to you. Just try to recall. Similarly, W12 and 22 also suggest something. So how do I write it in the matrix? The same notation has been followed over here. Right? So in this, we are just to bifurcate. Later on, we'll neglect that part. You see W11 on the top, I have written 1, 1, etc. Okay, that says that just to make you comfortable with this notation, the one which is written after I write a coefficient, I write 1, 1, 1, says that it is corresponding to the first. Okay, then we have another set of values here. So you see, it is also W11, W, because, right, there is a 2 here just to identify that, okay, it belongs to the second layer. In the sense, first layer, I have something, then the second layer. Again, since there are only 2 neurons over there, two neurons at the input, still can be represented as W11, W12, 212, because initially we are still getting adjusted to this mathematical representation using the matrices. So W11, 12, I'm able to understand. If I give a new notation, right, that may become difficult. So I'm still retaining W11, 12, 21, 22 itself. Just to bifurcate, I'm using 1 at the on the top just to say that it's belonging to first layer, 2 for the second layer. Okay, so just see this, and if you have any doubt, please let me know. You can ask a oral question as well. So just check this and check. All right, so this is the calculation corresponding to the V1 for this and V2 of this, not activated yet to be. You have to perform the activation yet. Okay, it's a simple calculation. So W11x1, W12x2. That's the first thing. W21x1, W22x2. That's what is this value. So you see, we are directly implementing that as okay. I hope you are comfortable with the matrix representation. Because we are using the matrix representation, it becomes easy even if you want to write a code. Right? So anyway, so I'll come back to the coding part slightly later. We have something to discuss in this part. Okay, so little bit of theory we are going to discuss now. Then at the end we'll go for. Okay, so let's say we are comfortable with this now. So I'll move ahead. Now, what we are trying to perform here is the forward propagation. This method is called as the forward propagation because input is given. How the input gets processed by multiplying by a weight and using the activation function, get a partial output, that you will feed it further forward, right? So it's a feed forward. As of now, it looks like a feed forward. Okay, but I don't see any connection from the output to the input or output to the any other part of the input, so that you can update, right? But you see, the rule or the equations are written in such a way that, right, from output we are able to update the weights. Okay, pretty much similar to the delta learning rule which we have used. Okay, so before that, let's look at the complete equations. Right, so these are the remaining equations. Just look at, so I think you may have to refer to this as well. Right, so these are the weights. Just try to remember the weights. Now I'll show you the equation. So partial values are there, the whatever you see here, they are the values you get as a partial thing. It's not activated, so you activate here, use a activation function. So this v1 v2 goes into this, apply the phi activation function, and you call that as the output of your first layer. Right, same thing should be repeated again, because now consider these outputs of your first layers as input, so that you can perform the similar job over here. Right, so here we are going to do the same thing again, since our notations of weights are going to remain same except that one or two at the top. Right, so now I can proceed with the same notation. So what you do, right, I will use the second set of weights w2 multiply by the outputs of the first layer, so that you can calculate this. This is v1 v2, which means, right, I'm those are the partial outputs corresponding to the final layer, because we just have one hidden layer. Right, input goes to hidden layer to the output layer. Fine, so short form notation is this, where w2 is the second set of weights. I think that should be fine. Let's proceed further. Just okay, quickly go through this last equation. Right, so it's pretty much same. v1 v2 comes to this, get activated, and you get the final output of the network. All right, so I hope no doubts in this. Right, pretty straightforward. Just understand the matrix representation, from where to where, what connection you have, and what weight are there. Right, so according to that, right, just remember w11 means what, that value you write here. W12 means what, remember that and write over here. That's all. Okay. Right, so now we move on to the important concept, right, that is the backward propagation. Right, so now we did what is the, it's a forward propagation, simple. Right, so give the inputs, multiply by the matrices, get the output, repeat this. So n number of times, where n is the number of times you have the layers. Like first hidden layer, get once, you do it once. From the first, whatever your output you got, to the second, do it again, like that. Okay, so that's what we have done now. So let's move further, wherein if at all this y1 y2 do not match. Okay, let's assume that they are not matching with my d value. Okay, in such case, what you are supposed to do, you have to perform what is called as the weight updation. Okay, now since there are layers here, from the output, if you simply apply the delta rule, you will be able to update only the weights coming to the final layer, not the layers before that. Correct? So I have to think about that. So any suggestion, right? So just think and try to give me an answer. What will be your approach in updating the weights before, for the layers before this? As of now, just think that right now I'm having only one layer, but in practical scenario, you are going to have hundreds of layers, not 100 neurons, hundreds of layers. Okay, just think, right? Whatever answer I'm trying to get now, right, that should be applicable repeatedly for all the layers until you reach your input layer. Okay, so you have 1 minute of time to think, and let's discuss that, and then we'll proceed. Okay, so what should be the ideal approach, right? So don't want any equation. Okay, just think about that and try to answer. All right, so meanwhile, I'll try to say paste one diagram. So that corresponds to the error back propagation. So again, whatever you see here in this part of the diagram, it just says that error 1 is corresponding to d1 minus y1. So we have a d vector now, because y has two values, y1. So y1 should be this, that's d1. Y2 should be actually this, that is d2. So d1 d2 compared with y1 y2, you get an error. Error is also going to have two components, e1 e2. Okay, fine, that's what I have shown here. And delta learning rule is the same thing. Delta 1 is equal to, you see, right, the same. Previously we just had one neuron over there, now we have two neurons, right? So Anybody has any idea how do we proceed, right? Because by using this delta 1 representation, definitely I can go ahead and I can update W11, W12, W21, W22 for the second layer, only where you wrote 2 at the top, right? That can be updated. So, but how should you, in what direction you should think? That's all. That's my fundamental idea behind asking that question. Anybody wants to attempt? Okay, I think I have till here. So the equations also you can see, right? Because they are corresponding to the delta 1, delta 2 values. Pretty straightforward method to calculate delta 1, delta 2 because we know the delta, right? So consider only the output neurons as two individual neurons, right? There are two inputs. To the final outputs, I have one connection. This calculates a delta. You can proceed with the updation of those weights. This actually is these two inputs are also connected to another neuron which is generating y2. There also you can do that. So delta 1, delta 2, pretty straightforward. We have this now. So the idea behind this is, let's say that we have an error here, right? This neuron made an error. So that error is because of wrong weights present on these two lines. So this weight is wrong, this weight is also wrong, because ultimately training means, so far we understood that training is complete if you have a proper weight update. Weights are proper means it will classify. That's what we know from so far whatever we have discussed. So because of that, now we will say if a particular output neuron makes an error, that is actually because of wrong weight updates, wrong initial weights, obviously, because initially you will make something wrong, then you will learn, right? So again, now you see this weight is not the only thing, right? Because I can see that the weight, this delta 1 is actually being used in the delta W calculation. What is delta W calculation? If you remember the equation of delta W, that is alpha into delta into the input of that particular neuron, right? So that input comes from where? That input comes from here, because it's this hidden layers output becomes input to your neurons, correct? So that x1 is also error, right? Only when x1 is in error, that x1 resulted in a delta W which is wrong, correct? The weight updated itself is wrong. That's why it couldn't make a proper decision, right, for a given input. All right, so we understand that there is some error at these outputs. Okay, now you compare the same thing here. We had an error here. We actually considered its previous layer's outputs, right? Right? We are saying that, okay, because your previous layer's output is wrong, I got my current weights wrong. They didn't get updated. So you see, whatever situation I'm right now I'm considering, the same situation can be extended to its previous layer, right? So error in this layer is because of the output in this layer, which is again because of wrong weight updates in that layer, corresponds to the input to that layer. Maybe in this case, I reached the input layer so quickly because I just had one layer at the middle. But if you have 10 hidden layers, this process continues. Output error because of the error in the last hidden layer. The last hidden layer's error is because of the error in the previous layer. In the sense, the output of that layer, output resulted because of the wrong weights. Again, the same thing, right? This actually you can see if you consider the mathematical process, right? The weight updation should be the weight updation happens ultimately, but before that I should consider why that error happened in the final layer. That is because of the previous layer. I should consider that layer considering its previous layer. Like that, you keep repeating calculation of error in each of the layers, right? Starting from the output layer towards the hidden layers, finish all the hidden layers and reach your input layer. Until there you should do this. Now you see the error is, right, considered to be propagated. Final error occurred because of the error previous to that resulted because of its previous layer. So now you pass through all the hidden layers until you reach the first layer. First layer is the input. Okay, input layer means inputs. Fine, those input values will also come in the equation at a later stage. Okay, this is without any equations. I tried to convince you that, okay, this is what we are going to do next. All right. So just think about it. And if you have any doubt, I'll try to clear now. But ultimately, when we discuss with the equation, definitely it is going to become more clear. All right. So, okay. So we are open for questions. Any questions?
So basically using some bias which will be updated and used to like, okay, adjust the weights.
Yes. Even if you are using a bias, right? So we will be considering that as another input with value 1. That's all. Okay. So you fix the input to be 1. Okay. I'll just try to write. But practically what we have seen when we jump into the deep learning concept, right, the whole concept of the bias was lost because, right, the neural network has so many layers to compensate whatever extra biases we have, right? So that's what is the ultimate thing. But anyway, so since you asked the question, I'll try to uh, write something, right? So you can consider that there is a input value equal to 1, and this 1 is given to each of the neurons. Okay, so here whatever you write itself will become the b value, the bias value, like b1 b2, right? You can use the b1 b2 also to for a calculation purpose, and you can update that. So this was something like this was very important only when we had very few neurons initially. Okay, but again in some examples I already saw that we never considered bias. So bias was there are actually two cases. So people think that bias is necessary. There is another group of people who think bias may not be necessary. All right. So it depends on their way of coding. That's all. Right. Was that the question or anything else to be added?
No, sir. Okay. I think clear.
Yes, sure. All right. So now we have a fundamental idea what we are going to do. So starting from output, in the sense output layer, I don't have any other method because so far I know only one technique, that is delta. Right. What I can do, I can calculate delta. So you see here I have written the calculation part corresponding to delta for both the neurons. Should be pretty much straightforward. This equation we used it. All right. Now you see, I'll slightly move ahead and I'll try to update those weights which can be updated because of these values delta 1 and delta 2 which are present over here, right? Because of these two these two delta values, I can update the weights over here. That's for sure, right? So how do I do that? Let's see. So same equations which we were considering so far, right? So same equation I'm going to consider, and okay, so let's see how it's going to look like. All right, so let's see this. In the sense, now our idea is that I have these values with me. I can update you these values, let's say, right? And that should lead, because now I'm able to calculate some error here, right? So maybe that E1, E2 can, because of the E1 and E2 I got delta 1 and delta 2, right? So this delta 1 and delta 2 will lead me to this, right? Using which I should be able to calculate the delta 1 and delta 2 of my previous layer. Then only I can say that, okay, I use those delta 1 and delta 2 of the hidden layer so that I can calculate further, right? So this should be the idea. Now I have to bring the mathematics, right? So how do we do that? We'll see. Okay, just read the sentence written over there. That makes things very clear. So error of a node is defined as the weighted sum of the back propagated deltas, right? So now you see these weights are wrong. So if I try to multiply the delta 1 and delta 2 of my final layers with these weights, somehow I should get a component of error. That is what portion of this delta 1 came from this is what I want. Similarly, what portion of this error came from this is what I want. That's what are the two values, delta 1, 1 and delta 2 of 1. Okay, correspond. The one says that it is the first hidden layer, because in this case only one layer, so we don't have it. Yes. Okay, so I hope the notations are clear. So my idea is that I use the delta values of whatever I know, multiply by in some way I need to multiply by the weights, because I move like this from the left to right, input, multiply by weight, I got output. Now you see we are doing the reverse, in the sense I have outputs, from there I got an error, into the weight, I should get the corresponding, right, what you call as the deltas of my previous layer. I can use those delta values and I can proceed backwards. This is the whole idea. All right. So just try to look at the equations that I'm going to write now. Okay, so just see this. Right. So corresponding to this particular diagram, I'm trying to write what is the error, because you see it's the same process. I'll try to repeat. I have a error. That error I converted into delta using the standard equation. Error to delta equation, right? You just try to recall, right? You had an error, you converted into delta by using the phi dash of the activation function's differentiation of that particular node into the error. So this is what I'm going to repeat now. If I get an error, I can convert the error into the delta of that particular layer. So we are trying to do the same job here. Okay, so just understand, I had a E1, E2 converted into delta 1, delta 2 using the equation. Now I need to convert these delta 1, delta 2 into the delta 1, delta 2 values of my previous layer, for which I need the error E here, E1 and E2, E1 of 1, E2 of 1. So you see, how do you calculate? Look at this. So it's actually, so this error I am calculating is because delta 1 into W11 into W21 into delta 2. You see here, that's the simple equation. I'm just simply propagating backwards. Previous equations are completely different, right? Don't get confused with what we did earlier when we calculated the output. You see, this value is calculated from these two. Okay, now it's not that case, right? This value, the error is calculated because of these two, that's all. Okay, so same thing is happening in the reverse direction. So the positions of your W1, W2, whatever we used earlier is different. Okay, I'm coming to that point, but as of now, just understand. Okay, mathematics. Right. So similarly, this error, I'm saying that the error that is located here, right, because of which I got error in the next layer, that E2 component of the first layer is nothing but, just see this equation. This is nothing but this delta value multiplied by W12, this value multiplied by W22 is what we have. Okay, so once you have the E1 of that particular node, I can convert that into delta 1 of that node simply by multiplying with the derivative of the activation function. So that it makes sense now, because since we already have selected a standard activation function, I know what is phi dash. I just need what was the V1 over there. If you know what was the V1 here, because when we calculated in the forward direction, when the inputs are clubbed here, we got a V1 there, right? I just have to remember that V1 I need to substitute, that's all. Okay, so this is the meaning of what happens in the, as I propagate from the output to the input, this is what is going to happen. Okay, fine. So now what we do, this whole process should be actually repeated further. But before that, let me try to write say the matrix notation, which makes more sense, right, whenever we go for programming at a later stage. All right, so I'll just try to write. Maybe this is going to help us. Right, so let's see that. So see the equations which are above and try to convert them into the matrix which is over here, right? So what's the conclusion? It is actually the transpose of the previous matrix we used, W11, W11, W12, W21, W22. That was the original W matrix. Now you see it actually simply got transposed. That's all. W11, W21, W12, W2. So right, so from this I'm writing this equation. there itself I observe, I compare this with the other W which we wrote, that is this W. Okay, just compare it with this and you will be able to understand that whatever is happening here is the W2 transpose. So from the output to the first hidden layer's error calculation, we are still using the weight matrix in a transposed notation. This is very important. That's all. So calculate the delta of output, multiply that out delta values with the W2 transpose, you get the error values of the previous layer. That errors can be converted into individual deltas, right, by simply multiplying by the derivative of the activation function, right, where you substitute a value v1 over there, partial output of that layer you obtain during the forward calculation. So, right, so this is what is the whole idea. Now you see I have a delta 1, delta 2 once again of the hidden layer. What I can do, I can repeat the process, right? So that delta 1, delta 2, right, use a previous W1 in the transposed format. W1 transpose into this delta is going to generate the error of your previous layer. So that previous layer, if you reach the input, no problem. If you have not reached the input, further calculate the deltas of the previous layer, right? Using that, first you get the error, then delta values, and keep proceeding. So this is the overall big picture. Mathematics is just this much, no complications, right? So how the error propagates and what exactly is going to happen, right? We need to understand. So for that, I try to take a very simple example of only two layers. Only two neurons in each of the layers, input, hidden, as well as the output. Okay. So any doubts so far? Please let me know. Right. I have some points to understand over here. Meanwhile, if you are asking any question, I'll answer that. Otherwise, we'll discuss about this now. Okay. So just if you don't have a doubt, please go through these points over here. Right. So whatever I mentioned, it's present over here. Right. So if you have more hidden layers, keep repeating this. Right. Once you are fine with what you call all the hidden layers getting the values of delta, now you see you can use those delta values for your weight updation. Correct. So initially our problem was we had no idea how to calculate the previous values of errors, how to update the previous weights was our problem. Correct. So only one layer I can do something. Now you have idea that I can calculate the delta values of each of the layers previous to your output. So once you have the delta values, apply the delta rule, because delta rule works pretty much fine for each and everything. It's a tested rule, right? So you see ultimate equation finally for each of those layers, right? The weights are updated using the same equation. There is no change in this. But you have to consider the delta corresponding to that particular layer. That's all. You need to consider the delta of a particular layer. That's all. Okay. Once you are able to calculate that's why the previous step was very important. How I keep calculating the values of the deltas of each and every layer. So once that is done, let's finish. Right. Next, you simply apply these to calculate and update the weights. First, you calculate the delta W. That's the first equation. Use that to update. Use that particular weight, sorry, delta values to update the weights of that particular layer. Okay, so now,
excuse me, sir.
Yes.
Sir, which standard activation function we are considering here? Because delta is phi 1 minus phi into error. So what is phi? What is phi here? Which activation function we are considering?
The sigmoid, right? Only for
okay.
Sigmoid.
And we are changing the activation function value is still phi 1 minus phi.
Sorry,
we want
which point you are asking about?
So this delta I value is phi 1 minus phi into error.
Correct. That is happening only if it is a sigmoid.
Sigmoid. Okay. And if we are changing,
it will change.
Then it will change.
It will change. You have to calculate and keep it right. Okay. So right. So depending on which activation function you choose, right? The whole concept will change because in my calculation,
because of activation function, yes.
Because of that, delta value requires that phi dash of whatever, right?
Right.
Depends on what phi is.
Okay, sir.
Okay.
Okay.
Right. All right. So fine. So now I have it's a quiz. All right. So I want you to tell me something, right? I want you to give me just guess an answer. No need to give me an answer. Just keep thinking. I'll give you some time to answer. All right. So I want. Okay. Okay. So let's consider this particular diagram, and I'll ask you a question now. Okay. That is. Okay, so consider the only the darker portion of this particular uh, diagram. We are talking about this. Okay, so now my question is that I want to update the W21. W21 is this weight, okay, of a second layer, right? So I need an equation something like this, where the delta W should be written in the form of alpha into delta into the X. Okay, so just to make sure that you understood the whole concept, right? I want you to think of an equation. I'll just paste the equation in once we pass on the time. I'll give you 1 minute of time to think, right? I want an equation in that format, Wij, that is W21. So W21 equal to, definitely, right? You know half of the equation now. W21 equal to W21 plus, right? Don't write a delta W. You just write something here. Alpha, assume some alpha, you can keep it as 0.9, 0.1, or if you don't assume a value, keep it alpha itself, no problem. What is this delta you are going to write? I want. Okay, look at this diagram and you are supposed to write. Okay, and what is the xj you are going to write is also important for, right? Actually, fundamentally, I'm looking for these two values, right? The delta I and xj is what I want. Okay, to be filled. So I want an equation W21 equal to W21 plus something, right? Just think of that equation. Just keep it in your mind. You don't have to give me an answer, right? After some time, I'll paste that answer, right? So that you can verify, and then we'll discuss if you have any doubt. Okay? Yeah. Okay. So just compare your answers, whatever you have decided. Compare that with this one. Okay. Right. So let's compare with this. So I had a Wij equal to Wij. So that's definitely W21. My question was about only W21. So W21 equal to W21 plus. Assume that there is some alpha. You can keep a value. Otherwise, that's fine. So the delta should be the one from where this, okay, that delta 1 corresponding to delta 1, I have an error. That error is because of wrong updation of this W21. So I should use that delta, because of which or to which this is connected. So definitely the delta value should be delta 2. Okay, let's come back to this equation. And
Sir, here Y11 or Y2?
I'm
Because
coming to-
the
I'm
output
coming to-
is, yeah,
I'm coming to
okay.
it, coming to it. Okay, So just consider this. You have this equation. This equation was simply corresponding to the delta learning rule. Okay, delta learning rule says that if you have a particular output node that gives you an error, you should consider the from where the input comes to that. Correct? To that node, from where you get the input, that input value you are supposed to consider. Correct? Now you see, in the forward propagation, what is the input to this node? That is y1, right? Correct? Because I had a v1 here. That v1 I activated using the phi function. I get a y1. That y1 acts like input to this, right? I hope that answers your question, right? You answered whether it is a different one. I have to write y1 only. That's why I'm writing y1 here. That is the input to this, right, particular branch. I hope that is clear. Any doubt? So the general, what you call the general delta rule is what you see here. Okay, this is applicable. Just think that whenever you are confused, you think that okay, there is one output node and inputs. That's where the delta actually originated from. So it says that if you have a output node which generates some error, we calculate delta. That delta is used to update these weights, right? Because it uses that equation, right? I need a calculator change in the weight. The change in the weight uses some learning rate alpha into the delta of that layer and the input on that particular line which you had given at the during the training. That's all. Now you see, take this as a simple one single output neuron, which means if you want to update this weight, I should consider the old weight plus change in the weight. Change in the weight is nothing but alpha. That's what you can see here, plus the delta of that particular line, that is this delta, and the input you give to that during the training. That's nothing but this. So now, but I'm actually going in the reverse order. That's yeah. Please take your time. Any doubt you have, let's clear it now itself. All right. Okay, I'll try to paste another diagram here so that that becomes easier for you to do the analysis further. Whenever you get confused, just compare with this. Okay, so all right, so has nothing to do with this question. It is a general one for that is applicable for error background. You see, when I do the forward calculation or the forward propagation, right? I have a v over there. Pass through the activation function, you get 1. Okay. During the reverse calculation, I have an error present at a layer, right? That error, I should pass through the function with the derivative of that. So that's the whole concept, right? Take a derivative, multiply by error, you get the delta as the output. For a layer, when it propagates in this direction, v to y conversion happens. Through the same neuron, when the reverse calculation happens, you have error. Multiply that with the, in the sense, you are using the activation function's derivative, I'll be able to calculate the delta of that. So, right? So just remember this. This is going to help you a lot. Any question on this above said point or the diagram which I asked as a question, right? Any doubt? Please let me know. Okay, so I'll ask you another question. This is the second quiz. All right, I gave an answer. Sorry. Okay, so I wanted to ask what was a W11? How do you update? Okay, so just see that, and if you have any doubt, please ask me. So the question is, how do you update W11? So W11 equal to W11 plus that delta W1. So right, we are trying to answer that here. Just look at that, and if you have any doubt, please let me know.
So cleared.
Clear, right? So
Yes.
we apply the same rule everywhere, right? So just remember the main point I mentioned over there. That's only this set of these two equations, right? So apply that. Just think what is xj stands for. All right. So that stands for the input I'm getting for this particular weight, right? So in this case, that is x1, right? So you see the equation simply becomes equal to x1 over there. And which delta, right? You are considering the delta of the layer to which this W11 is connected, right? So like that, use the W1, right? Multiply. Actually, we don't do this mathematics at all, right? We are not writing the code for this equation, but in order to understand, check that whether you have understood the concept. This is what these equations are supposed to be written. But definitely, when we write a code, right? After this, maybe we'll go for a break, maybe now. So after that, we'll start writing the code for this forward propagation as well as a backward propagation, wherein we will never use any of these equations. Okay, that will not come in the program, because what we are very comfortable with is this matrix representation, right? So that actually takes care of everything, correct? So we will never write any code, because that kind of approach, if you use for a programming, it's going to be very tedious. Because right now I just have simple neural network. What if I have like hundreds of neurons in that? So everything I need to write in that way. So we'll avoid that. All right. So we simply represent everything in the matrix format first. So once you have a matrix with you, right, you definitely do a linear algebra, keep multiplying, right, and apply the activation function to get the outputs. All right. So I hope that's clear. Now I will. Okay, I'll just give. We'll make a plan so that we can come back and we can directly do the program of the back propagation. So I'll just give a question now. All right. Right. So the problem that we want to solve is it still remains same. All right. So whatever I don't want to change the problem, because later on, whenever somebody wants to make a comparison, it becomes easier if I keep the main problem as same. Right. Right. So this is our target. Right. So I just want to, right, build the network. Right. Again, it should be very clear by now that we are going to use at least one hidden layer. Okay, so just think when you go for a break, if possible, that what will be the architecture, what will be the structure of the neural network which we are going to use, how many inputs, how many hidden layers, and how many outputs are, right, the fundamental things we need to decide initially before I go for a network building. Okay, so that's what is going to come next. I'll ask that question to you, right, when we come back.